Okay, so welcome everybody. Today is the third day from the third out of 12 days of NeurIPS. We covered the flyover so far. We saw what happened with agents. And today we're gonna see what was discussed about foundational model for tables, or I like the term language model for tables, but people like also use foundational model for tables. So, okay, as I mentioned before, there were three separate events, which I'm going to cover all of them. An expo, 1 hour, another expo, and a workshop where we also had a paper. So there was a very comprehensive expo called tutorial from Capital One that seems to be very focused on this domain. And Doron Bergman gave this nice talk, which I have the link. I think when we talk about deep tabular models, we mean three things: MLPs, transformers, and language models. I just like FYI, the difference between a transformer and a language model is that a language model is a heavily pre-trained transformer. Okay, but you can always use a transformer as a predictive model on its own. I mean, we kind of forget that the attention all unit paper introduced a transformer, but the first pre-trained transformer language model was BERT that came the next year. Okay, so we start comparing, shallow models like XGBoost, which is kind of the king queen of predictive models, with MLPs. And it's kind of day and night. You can see here random forest and XGBoost beating almost everything in different tasks. Now, let's see a couple of points. Now, it started becoming and working on par with some deep learning models when the size of data becomes very big. Okay, that's where we start seeing some competition. But in general, the biggest problem, like people have come up to the conclusion that the reason why tree models are hard to beat is because deep learning models have a property which is very hostile to tabular models, which is they are rotation invariant. And the way that the term rotation invariant, what it means that if you permute the columns, okay, that's not a problem. So they are okay with permutation of columns. While of course, a tree model, if you train a tree model and you permute the columns, it's not going to work. And just to give you,
why is it so? I mean, if you have a relation, you don't care if it's a first name, last name, or last name, first name.
Yes, that's exactly. Tree models are actually relational models, but MLPs are not, because if you think about how a neuron works, it just takes a weighted dot product, or a dot product, a weighted dot product. So you just do a dot product of the node weights and all the values of your columns, and then you collapse it. You take a sum with a
max. So I think even at the instance level, if you permute,
yes, exactly,
it is invariant, whereas in relation, not the case. Yes,
and exactly, and that is a problem, because what happens is if you have a column that has, let's say, noise or irrelevant data, and then in the first layer, it's going to get mixed with everything else, and then it takes several layers and a lot of effort to recover it and reject it. While, if you have a column that it's very noisy, the tree model won't find any information. It will keep kind of rejecting it. It will keep pushing it. It probably will never use it. So that kind of mixing that happens early on between features that they are irrelevant or even noisy, it's a big problem. So you can see that over here, tabular datasets contain many uninformative features, and MLP-like architectures are not robust to uninformative features. Aggressive regularization can help, though. Now, for many years, people believed that the categorical variables was the problem. Now, obviously, if you think about the transformer working with text, and text is a highly categorical data set, we know that that's not a problem. We can solve that with embeddings. Another kind of finding, takeaway, and by the way, I'm just touching upon this, giving you some thoughts. It's quite a detailed presentation. That takeaway is that XGBoost requires substantially less hyperparameter tuning to perform well, which is a significant benefit for many real life scenarios. And again, here benchmarks. You probably see it small in your screen, but you can go to the presentation and see more on that. But yeah, the point is that people tried many years for MLP type models. It didn't really work. Now then, at some point, they started using generative models like the DPM, for example, that using diffusion. And they did that for data imputation. And in some cases, this is a technique that I believe we're using in images and clip, where you take an image, you corrupt it, and you're trying to train a model to make sure that they are the same. I remember I've seen this paper in the past. This is the SCARF paper, yes. And then you use these features into trees. I mean, people tried the Excel former, but so it uses a transformer over here. It kind of attacks a little bit the rotational invariance. And then this is Saint. This is one from Saint, from Capital One, that uses self-attention. Again, the idea over here is you are trying to address this problem of rotational invariance. There's lots of details. I wouldn't want to go into many details. So, these are some other models, like the generalized additive models, that they basically try to fit an MLP separately for every feature, for every column, to learn a representation, and then try to adjust them better. But it also didn't work very well. Then what they did is they took decision trees, and after you train the decision tree, decision tree is basically if then else rules. So you take this if then else rules and you replace them with a sigmoid. So you make it differentiable. They called it oblivious decision trees. I remember that paper too. And yeah, it worked, but it slightly outperforms XGBoost. So interesting idea, doesn't work really well. And then people even tried CNNs, which sounds counterintuitive because in images you assume that the CNNs, the neighborhood is kind of correlated. It's relevant to you when you're looking at a pixel. Of course, it only worked on. There are technically tabular data are the gene data are tabular because they put them on a table, and there is some locality, and they got some decent results. But you can't really use it on other data sets unless columns have some kind of correlation. I think the most successful that we've seen so far is the prior fitted networks, or the TAB-PFN as we know it. We talked about that a little bit on our first talk, or first day. So TAB-PFN is an interesting idea where you create random graphical models, so random predictive models if you want, and you generate data and you train a fairly lightweight generative model. It recently became, TAB-PFN became a company. It's called Prior Labs now. There's a TAB-PFN version 2. And what happens is it has some limitations. You can only fit 10,000 points on the prompt. And we know so far that it works well with the data sets that are mainly numerical, maybe with a few categorical columns. What else can we say here? Another approach is that you take, you just take the language model, you take the data, the columns, and you verbalize them. and you just go and you pre-train a language model treating the tabular data as text. Okay, we're actually going to see Tabula later on that according to the authors work well. Now, one of the problems that we're going to see later on is that how do you represent numerical data? Because here, I think we're going to see it in the next slide. When you when you represent them as numbers, as text, you lose the ordinality, and that's a problem. And people tried other things, like they use some kind of decision trees to discretize them. Okay. Now there's another technique of mixing categorical and numerical data. There's a lot of details, and we're going to see another paper later on how it deals with that. In general, there's a lot of approaches. So, I mean, another thing with the feature transformer is you make every number a separate token. That's why it's called feature tokenizer. So you kind of explode your tokenizer over there, and you do some kind of linear transformations. That's kind of like another interesting technique. It doesn't seem to be a solved problem so far. Now, it's been a long trip with a lot of papers, and it's not a solved problem yet, although we had some breakthroughs this year, as we're going to see. And here, kind of like the open problems: data, encoding, and foundation modeling. So there's still people, when they use transformer, they don't use the traditional transformer. There's a lot of variations. There is this idea of continuous generalization of trees. And even for training, people use, as we're going to see, traditional pre-training, next token, but there's also some other techniques. And some speculations for the futures. Are we breaking rotational invariance enough? Yeah, people claim that dropout, helps in that direction. But other people are trying to use techniques from computer vision, like augmentations. And there's also this specification, maybe a quantitatively weak effect for ReLU activation in particular. So, they're disputing do we need ReLU or we need something else? So anyway, it's still an open problem, but as we're going to see later, we're getting there. And of course, there's a lot of references that you can go through. This expo had a lot of, actually 33 references. I have all of them here, so you can go through and learn more. They're very interesting. Now, surprisingly, I don't know, should I say surprisingly, but I was surprised. I didn't know. Autogluon, which comes from Amazon, seems to be, or claims to be, a very complete solution for tabular models. And Autogluon is not new. Is something that started in 2018, and the motivation was to kind of address these monsters that dominate the machine learning competitions. I feel circa 2018, 2019 at Kaggle, people were heavily engaged in this competition, so they were creating these extremely complicated models to win some considerable amounts of money and get glory. And it was hundreds of models, thousands or maybe tens of thousands of features, stacking, bugging, and people worked towards packaging all these models and trying several combinations, and basically give you 3 lines. So if you have a predictive model, you download Autogluon, you load your data, you say fit, and then predict exactly the same way you would do it in scikit-learn, and basically hide all that complexity. And it did have very good results. I think in 2024, Autogluon has become the ML community go-to tool for competitions, finished in the top 3 in 16 out of 20 live Kaggle competitions in 2024, like tabular competitions. That's like really impressive. And here's some other statistics. Equivalent to 19 Kaggle gold medals and 1 Kaggle silver medal. I don't know what it is here, this equivalence, but you can tell that it's really interesting. And recently, it introduced also tabular foundational models like the Tab PFN that we saw before. It's their own implementation. And it says outperforms all public existing singular tabular models, including Tune, CAT, Boost, and Tab Forest PFN on datasets with less than 10,000 tracing samples. Supports both classification and regression. More details to come in a paper. They also introduced the Tab repo, which is an offline ensemble evaluation. So they have, I don't know, thousands of data sets and hundreds of models, maybe more, that they evaluate. And it kind of like helps you choose, like based on the data set that you have, like they go and they select models and you can ensemble them and you can get better results, or you can benchmark your own solutions. I'm not sure I understand exactly how it works. It says you start from an empty list, simply select the best model to add to the existing portfolio. I don't exactly know what the portfolio is. That achieves the best average test score on the training data sets and repeat n times for portfolio of size n. So I see something on the... Yes, these are all, they work on a single file. Yes, that's what I'm asking. They're not in multiple. So yeah, I think I should make that clear that everything over here is on a single table. Now, they work very actively on that, and they're coming even with stronger and faster tabular models coming up. 2025 TabFN version 2, GPU support, better scaling with basically increasing the context window, and some improvements on Tab Repo 2.0, and much more. And AutoGluon Assistant. So AutoGluon Assistant is an interesting thing. It's more like the OpenAI assistant, where you drop your table and you give it a prompt and you start asking questions, and you can say task understanding. So you give what the objectives. It generates features for you, and then it predicts model. And you see some impressive statistics. AutoGluon Assistant benchmark set up features 40+ Kaggle competitions with diverse problem types. With only 4 hours of runtime, AutoGluon Assistant achieves a medal on 28% of Kaggle competition. So again, think about that. It's your data science assistant, where you put things, it runs some things, you basically give it some feedback, and you keep going on. So this is real predictive models with your data. But they go beyond tabular data. They have a stack for time series. And they have, that's kind of all we know about that, the probabilistic forecasting. But they also have pre-trained models, transformers for tabular data. Let's not forget that a transformer is a time series forecaster predicts the next token by design. And actually, you can fine-tune these models. So you can take Chronos, is their language model or foundational model for time series, which you can fine-tune, and you can also add covariance. So when I say fine-tune, you're just giving the next the time series, but you can also add extra features on that. Or it was raining, or there was a festival, or something else. And their plan is to kind of create a super generalized drug. Okay, so you can think about predictive task as another modality. So when you talk about multimodal language models, you can have images, text, tabular, document. So these are all the modalities. And then you have a foundation model, and the task could be answer question, or segment an image, or do NER, entity recognition, or object detection, or regression, or classification. Okay, so this takes us closer to a more complete language model. And then we move to the table representation learning workshop, TRL. let's see a few statistics. These are the tables. Tables are everywhere. Ranking scores per DMS type by DB engines. So relational data. Obviously, relational databases are the ones that they dominate. And data sets are mainly in tables. I don't think I need to motivate this group over here why we need tables. And tables are driving so many applications. So we want to make all these data tasks, tabular tasks, better and easier. And you can see we've been participating in this workshop since its beginning. In fact, we sponsored the first year, and you can see that there's a growing interest. And here was the keynote from, I don't know if I'm pronouncing this, Gael Varacquo, maybe. He's one of the co-founders of Scikit-learn, and he works for INRIA. And okay, here he does motivate the need of tabular models. And I'm just going to stay on this quote that says, in data science, 80% of the times spent on to prepare data, and 20% of the time spent complain about the need to prepare data. Okay. Basically tells you that running the predictive model takes no time. And here you saw that kind of that plot before. Deep learning, this is the gap, and it kind of motivates some of the problems that the feature distributions are all different, very non-Gaussian. The trees don't care, and also the main problem is that there's not really a similarity or Euclidean distance. So basically, what it's telling you over here, it's very hard to find a geometry for the data. And that's more like a philosophical discussion, but deep learning implicitly has or tries to discover a complicated geometry. And that geometry is neither natural nor vectorial. So it's not neither smooth nor vectorial. And that is a problem for MLPs in general. And here's kind of like an interesting statistic that I didn't know. Of course, we do know that deep learning struggles on tables. That's fine, but you think PyTorch is popular, 34 million monthly downloads, but actually Scikit-learn still has double downloads every month. People still so. But if you think that Scikit-learn is the way people spend their time, no. Pandas is even more popular. I think 3 times more, 3.5 times more. That's basically tells you about all the problems with dealing with data. And people said, and this is a slide that you're going to see several times during NeurIPS, the success of neural networks. How did we make neural networks successful? By taking large data, okay, and pre-training a deep model, a transformer model. Not in vision, we had different models, but it's large data and pre-training, self-supervision, in other words. And the question is that, can we repeat this recipe in tabular data? And here it takes a simple problem of predicting the price of a property. And it says, okay, maybe we need to enrich that that data set with more tables. So that kind of goes, Elias, what you said before. Now we have to deal with multiple tables. So that's the first work that talks about tabular representation with data being in multiple tables. So it's truly relational. And somehow when you're fine-tuning or pre-training, it needs to be able to join that data. Okay, so you see how this, these data are coming as part of the features. The problem is that the representation might not be the same, and doing that, that's why it says that the richer the data source, the worse it gets, kind of like this joining process. And the data are also very heterogeneous. They're discrete, and we kind of like face a problem of how can we bring them into the same space. And he talks about different embedding techniques, especially dealing with how we embed numbers. And they came up with this vectorial embeddings called CAN, which is pretty foundational to the tabular model that they built, the foundational model they built, which I think is very interesting. I'm not going to go into the details. If you want, one of the detail over here is that the data is represented as RDF triples, as graphs. So it doesn't have to be RDF, in my opinion, but that's the best way of taking tabular data and connecting them is CAN requires to take, basically this is something that we've seen in GNNs, that the best way to represent relational data if you want to do predictive tasks is represent them as graphs. And you see here from tables to knowledge graphs. And they do this kind of like unfolding, and they take a knowledge graph. I think they take Freebase and some others. They apply this CAN type of embedding tokenization, if you want. And they created their first foundation model called CART, which, as you're going to see, it really beats tree models. So deep learning, beating. And here are the results. I'm just going to stick here, showing that this is CART kind of outperforming others, not by a lot. And here you can see it in a different graph. Okay, but that's kind of like the first approach. Now, one of the things here is more examples, and that does show that TabBFN does still much better when your data is mainly numerical. Okay, so there's not like a clear winner, like we don't have a clear winner right now. But the problem is at what cost? And, it's very powerful, you should try, but it's resource hungry. So, it turns out though that still if you combine trees with foundational models like CART, you can do even better. Okay, and they also have another tool called Scrub. So I don't have time to go into details. It's kind of like a lightweight tabular model. And there was also another model that people published. It was an oral presentation called Tab Sketch FM. I think it's kind of like in the weeds. And here are the references on that. Okay, what you should get from this talk is that yes, we actually have a foundational model that does better than tree models, and the more you see, has 6 million entities. The more data we feed it, we expect to get better results. Okay, and here's the presentation. So we're kind of like, we're gonna take a break from foundational models and move into change a little bit gears to relational databases. So it's a talk from Matej Zaharia from Databricks and Berkeley, not Stanford anymore. And it was an interesting talk. I highly recommend it. He gave that talk with the title "Lessons from Building Natural Language Query Systems." So it's basically text to SQL, and basically, what you should get over here is that before you answer a query, they have this paper called "Enhancing LLM as it does with Grading Nodes," and basically this is an annotation of your database or an automatic annotation. So you see here, how do I drop all tables in a Unity catalog schema? And so you basically take different from your logs different queries, and here you annotate it about giving it instructions. And then there is this other paper they did, the Lotus, which I find it very interesting, where so far we're used to having a relational database where you do things, let's say in SQL, in a structured query format. And then you have language models that you answer questions in a structured format. And the question is, what if you have, and when people talk about, RAG, they think about either taking the question and converting that to a structured language, like a SQL query, or bringing the right side of documents and answering, try to answer from the documents. So what if you're trying to want to fuse that? And the way you do, they have this example over here, where you say summarize the reviews of the highest grossing romance movie considered a classic. And here you start writing your SQL query, and at some point you have like this special operator LLM, where there's an LLM that needs to filter its movie and decide whether it's a classic or not. Okay, so that's something that you don't have it into your database. And that's something that they did in 2024. Now, I just want to say that, back in 2021, we had a similar recommendation over here. And this is from a slide that I put over there in REL, where I say it's kind of similar. The question is, which startups received investment from funds that they were over 1 billion? And, this is a typical REL where you basically, those days we didn't have sophisticated language models, we had BERT, so you had to restrict your answer to be length 1. And it was basically a transformer that was, after you were funding all the investor funds that they were 1 billion, it was supposed to go and guide the transformer decoding to only consider, investors that they were in that subset. So that kind of like raises a whole question about how do you fuse, how do you create a query optimizer that decides, do I have to run the query first and then do the decoding and then run the query? And I'm just okay. So let's go to the next slide. Here are the references on Lotus. And then we're going to, I think this is, if I remember the last presentation. So this was the last presentation on the TRL workshop by Josh Gardner, who works at Apple. Surprisingly, Apple has a big initiative on that towards robust, reliable, and generalizable tabular models. Invited talk. And he basically, motivates everything in the in the same grounds with the talk that you saw from Gael. He basically says the same things, foundational model and emerging recipe. Can we just collect data and pre-train a model? And here's some interesting statistics about tables. This is so that the problem is hard. Like in image data, this is the test versus this is, yes, the test versus training, I think, accuracy. Like you basically see that you, actually, this is CIFAR test on CIFAR 10, and this is the 10.2. And you basically see that it generalizes well. It's very close to the, to the by sector. And this is the same thing for images. So you trained it here, or you train it here, and you did some perturbation, and you see how it generalizes. With tables, things are, this is the in-test distribution accuracy. This is out of test, and you can see that tables degrade fairly quickly, and that is a problem. The author here discusses some of the techniques. So just to kind of like distill that, he basically believes that the best choice is to just serialize the tables into natural language and train as a next token. Sorry. And then he tweaks a little bit the attention. So he makes it like, if you order your data in a way that there's some correlation, you can always use, information from previous, like in your attention, like if you put 10 rows at a time, they kind of like steal information from the other rows. And basically the model that they created is called Tabula. And Tabula, behaves really well. So, one of the very first question was that, okay, what if I go and I do a few short learning? So let's say I go take, I don't know, Llama here, Llama 3, 8 billion, and I put some verbalized rows. And I'm gonna do the same as if I had actually pre-trained a model like Tabula. And basically, it shows that it does much better. Okay, 8 times sample efficiency. I think I'm not sure if because it says 0 shot. So yeah, so here's this is the 0 shot. Here you can still keep adding things in the context and do better. But the point is that it behaves 8 times better compared to an untrained model. Here's a position paper that says why tabular foundational models should be a research priority. And I think we kind of covered that in the previous talk. And here's even more benchmarks from Tabula that you can go through, and they stress it under different transformation and noise. But what was really interesting is people were curious to see what does the language model learn, and they realized that the decision boundaries in these kind of toy examples are not very different from what XGBoost learns. Okay, so they basically pretty much learn the same shape here and there, which I find very interesting. Again, numerals are still a problem. They talk about it. They do claim that Tabula works on numeric data, and it does really well. They basically believe that you don't really have to do anything. You need to. It's fine if you use it as a separate token. Now that contradicts a little bit with what we saw in the previous talk, but I think the reason why we haven't seen like we see these differences because we haven't seen extensive benchmarks that they're pretty big. And I think once we increase the number of the benchmarks and the training data, this kind of difference in perception is going to settle. One of the things that I didn't mention, I think I've skipped the slide, is this talk talks a lot about compiling a pre-training data set. And maybe the reason why they behave better than CART is because they actually worked on a pretty big data set, 627 million tables, which of course they had to distill. It's much less what they eventually used. And everybody talked about the need of getting, a bigger pre-training data set. So that's something that the community is actively working. And here are the references. And we are on time. Next time, I think next time is going to be smaller. We're going to talk about scaling laws. Okay. And we are done for today. Thank you, everybody. I mean, I forgot yesterday I had another meeting. You can ask questions if you want. I'm just paused the recording.